Thanks a lot, Jonathan. Hi, everyone. Thank you for being here today. We're going to be discussing attack vectors in managed Kubernetes environments. So my name is Christophe Tafani de Repère. I'm French, living in Switzerland, and I'm working at Datadog, mostly focusing on open source and cloud security and container security topics.
Hey everyone, my name is Nick Frechette. I'm a security researcher also at Datadog. I specialize in AWS offensive security.
Great. So today we're going to maybe set the stage a little bit. We're going to be in the cloud, and we're going to use mostly AWS as an example, but we'll also talk about GCP and Azure. So we're going to talk about EKS, which is the managed offering for Kubernetes in AWS. And so in that context, we're going to be inside EC2 worker nodes that are running pods. And so we are trying to get from the standpoint of an attacker that has compromised one of these pods, okay, and that is able to exploit the vulnerability there, and who's trying to pivot to the AWS account, to the GCP project, or to the Azure subscription. So we're going to see a few attack vectors: remote code execution, server-side request forgery, arbitrary file read, and we'll try to see with each one of these, what can we do, how can we pivot to the cloud, from the cluster to the cloud, and maybe even sometimes from the cloud back to the cluster. So the first technique that Nick is going to tell us about is from pods to the cloud through the instance metadata service. But maybe before a bit of context, so when you have worker nodes in AWS, the nodes, they're going to need permissions to do things like pull containers, create network interfaces. So to be able to do that, the way this works is that your EC2 instance has a role attached to it. On the next slide, you will see that it's actually going to, the components that run on the node are going to get credentials for that role through the instance metadata service, which we'll see in a bit. And basically, the main thing that we're going to see is that if an attacker is able to access this instance metadata service, they're also able to get credentials. So Nick, maybe can you talk about a few attacks and how this can be exploited?
Yeah, absolutely. So there are a couple of attacks that come to mind in this general setup. The most likely one that you're likely to run into is something called a server-side request forgery. This is a common web application vulnerability where we're able to coerce or convince a web application to make an outbound HTTP request on our behalf. So in the example diagram we have here, we're able to pass in a URL parameter for the dangerousgoose.me domain, and that allows us to make an outbound HTTP request and potentially get the results of it. Now, in a cloud context, this has a particularly important outcome. By that, we mean that if we can exploit a server-side request vulnerability running on a pod in a Kubernetes cluster, we may be able to make an outbound HTTP request to the instance metadata service of the underlying EKS node. And from there, we could potentially extract the IAM credentials associated with that identity. So by abusing a pod, we can pivot off of it down to the instance metadata service of the underlying node. And once done, we can use those credentials to authenticate as the identity of that node. Here you see us performing the STS getCaller identity API call, which is essentially the equivalent of who am I for the AWS API. And indeed, you could see we're operating as the node instance role. Now, a quick tangent here that is important to note if you are a pen tester or a red teamer. This is a very well-known attack vector. This is something that is commonly taught. It is well documented. It's resulted in a number of breaches and compromises over the years. And as a result, there are a ton of commercial tools that have detection rules out of the box that will detect this type of activity. In particular, probably the one you're most likely to see, the most common, is AWS's own GuardDuty. GuardDuty being a managed threat detection service offered by AWS. Now, GuardDuty has two types of detections, or excuse me, two rules for this type of attack, an outside AWS detection and an inside AWS detection. The inside AWS one is a situation where you steal IAM credentials off of a host and then try to use them on your own EC2 instance. That actually used to be a way to bypass this detection by using your own EC2 instance. All that the detection was checking was, does the source IP match a EC2 instance that exists? And if yes, it's totally fine. But they have since sort of upped the ante on that detection, and now it will detect when it's in a different AWS account. Alternatively, the outside AWS detection is one where you use the credentials from your home address or perhaps a VPS that you own, and would likewise get you caught. And of course, this is unfortunate because as pen testers and red teamers, we don't like getting caught. There's certainly a lot of value in trying to evade detection. And theoretically, since it covers both inside AWS and outside AWS, the union of those two should cover everything. But interestingly, there's a bit of a forgotten avenue that we can pursue. If we use a VPC endpoint, which is, as the name implies, an endpoint you can place in your VPC, we can make calls to the AWS API while navigating through AWS's own internal network. And essentially, VPC endpoints are designed for situations where you have, say, a air-gapped network that still needs to talk to the AWS API. Now, the good news for us is that these endpoints don't trigger that GuardDuty detection. So by using a VPC endpoint, we can evade the instance credential exfiltration finding, both inside and outside AWS, and allow us to use those credentials without having to worry about the blue team coming and finding us. If you're interested, we have an open source project called Sneaky Endpoints that is a collection of Terraform scripts that'll spin up an environment for you, an EC2 instance you can use, as well as a bunch of VPC endpoints that you can start routing your traffic through and evading detection. Now that we have covered how to hide from the blue team and operate silently, let's talk a little bit about what we can do once we have those credentials. In order for your EKS node to perform all of its job functions, it needs to have certain permissions associated with it to do those. And they can be fairly powerful. In particular, out of the box, they will have the ability to list and describe all EC2 instances in the account. So, who needs nmap or any other type of reconnaissance script, if you could simply just list every EC2 instance and its associated IP address, allowing you to pivot from there. Additionally, they have the permission to pull all container images in the account. And this could be great to do things like steal source code, try and hunt for credentials, and more. And finally, if you're interested in perhaps a little more destructive activities, these permissions have the ability to destroy all network interfaces in the account, and you can certainly wreak havoc that way. Now, for a practical demonstration of how this would work, here we are abusing a web application to reach out to that linked local address and pull those IAM credentials. And once we have those credentials, we are authenticating with those IAM credentials that we have stolen. And then we are using them to authenticate to the Elastic Container Registries. We then use the AWS CLI and the Docker CLI to pull those containers. And one thing to keep in mind is that it is possible for when those roles are created to have excess privileges, or they may be accidentally provided permissions. So for instance, in attempting to provide read access, they may accidentally provide write access. And that might be an opportunity to potentially push containers as well. And I will go ahead and hand it over to Christoph to talk a little bit from the other cloud service providers.
Thanks, Nick. So on GKE, which is the managed Kubernetes version on Google Cloud, it's a bit different. The worker nodes by default run under the default compute service account with a limited scope, which basically means that you can get access to GCS buckets and the BigQuery tables as well. So it's not that privileged, but it still allows you to read a lot of sensitive data. And when you want to talk to the IMDS in GKE, you need to add a specific header, which means that exploitation through SSRF is much harder or even not doable. On Azure, it's a bit similar. So you will see on the screenshot below that this is an example of trying to exploit an SSRF on Azure. You need to add a specific header for it to work. So it's not going to work, which makes SSRF exploitation harder to achieve. And in terms of permissions, there are no permissions by default in the managed identity that's assigned to the nodes, but they get added iteratively as you add integrations. Now, if we go back to what Nick was showing us before, so we compromise, credentials from a worker node, and we are authenticated as a worker node. So we can just use AWS EKS update kubeconfig, and if we use kubectl, kubectl, how you want to pronounce it, we see that we are authenticated as a node. So what can we do from there? Well, one thing to remember is that worker nodes by default in Kubernetes, they have, in theory, a lot of privileges granted by the system node cluster role, but in practice, it's limited by something called node admission, which is a mechanism in Kubernetes that basically blocks a lot of actions from the worker node roles. So as you can see here, if we try to run pod, it doesn't work. If we try to enumerate secrets, it doesn't work. So what else can we do? So something to keep in mind is that the nodes who are running the kubelet, the kubelet is a Kubernetes component that is responsible for running pods. And one of the things it does is inject service account tokens inside the pod file system. And to do that, it needs to ask service account tokens to the API server and then injects that into the pod that it runs. So one way that the attacker can abuse it, and again, that's by design, is, so we are authenticated as system nodes. We're going to say, hey, I want to create a service account token for pod B. So for the service account token, for the service account that pod B is using. And then it means that you get this service account token back and you can authenticate to the API server as pod B. This was first reported by, I think, someone from Caliph. We link to the blog post in the slide, so the credit for that goes to them. Now, once you're here, this was supposed to be a short demo, but I can describe it as well. Okay, great, it works. So if we can we can keep it running. So we're going to see here, we exploit a server-side request forgery in AWS. You can see that we are using the URL of the metadata service that's specific to AWS. We can discover the role name, that's role that's used here, copy paste that, and we get back some credentials. So we can basically copy paste that in our environment really quick. And we see that we're going to be able to authenticate as a worker node, as we saw. Now, what we can do next is, again, if we use kubectl, what can we do? We'll see that. So what we're going to do here is the attack that I described before, which is first, we see that we don't have any permissions on the API server, or very few. Next, we're going to look at the pods. And if we look at the pods, we'll see that there are multiple pods. And we can ask to create a service account token for a specific one. So this is for the inventory service SA, service account. We get back a token that we put into a file. And then if we look at the permissions in that token, we'll see that these are very privileged. So this is an example of how being authenticated as a node, you can steal the credentials of any service account for a pod that runs on that node. Now, if we go to the next slide, this is what Nick was showing us before. If we go to the next slide, to summarize a little bit, so we were able to exploit either a server-side request forgery, either a code execution in a pod. From there, we were able to authenticate as a worker node by stealing credentials on the instance metadata service, right? This is what we saw in that demo. And from there, you could stop there, but you can also basically try to impersonate any pod that runs on the worker node. Again, that's by design. And you can use that in particular to try to escalate your privileges if there are any privileged pods or pods that have specific permissions on the Kubernetes API server. Now, what can we do? That's the question, right? So for AWS, we need to make sure that IMDS v2 is enforced on the worker nodes. It's now a default actually since a few months ago if you use Amazon Linux 2023. And for Azure or GCP, as we saw, since you need to specify your specific header, by default, you are not vulnerable. Now, this is for server-side request forgery. So this is only applicable if you want to exploit server-side request forgery. But if you have something like a remote code execution, you're going to see in the screenshot below that we have a command injection. So even if Azure has this metadata header that you need to provide, Well, if you have a remote code execution, you can do that, right? You can also use IMDS v2 because you can run any commands on the pod. So these things are very helpful to protect against server-side request forgery, but they are not helping solve the root cause of the issue, which is your pods and anything that runs in the pods should not have access to the node credentials, right? And so what does this mean? In practice, this means that in GKE, you need to enable workload identity, which is sufficient. So if you do that, the pods can still talk to the IMDS, but they will get back credentials that are scoped to their own permissions, not to the nodes. And on Azure and AWS, you need to explicitly block access to the IMDS. So these are two features that we'll see next, but enabling IAM roles for service accounts or Azure ID workload identity is not enough because it will add things to the pod file system, but it's not going to help blocking access to the IMDS. So this is, the TLDR of this talk is basically do that. Now, this is, for the easy case, if you compromised a pod, if you exploited a server-side request forgery, but there are many other things that you might run into, such as you were able to exploit a pod in some way and you get read access to some of the files. So Nick, what can you do from there?
Yeah. So far we've looked at pivoting off of a pod to go after the underlying EKS nodes instance metadata service. You might be wondering, is there some opportunity for us to take advantage of cloud identities provided to a pod? And as a matter of fact, there certainly are. Now, the first thing that may come to mind if you're trying to provide cloud identity privileges to something might be to use long-lived static credentials. In AWS land, these would be things like IAM user access keys. Now, these have been known to be a problem for quite a while for a variety of reasons. They end up getting stored in source control or perhaps even embedded directly into application code. And as a result, there's a high likelihood that they can be leaked. And because there is no expiration by default, if an attacker finds them, there is a high likelihood that they can use them. So hopefully your developers and the folks in your environments aren't using long-lived credentials. The much better solution would be to use short-lived credentials. These are ways of providing a particular application or service the ability to access cloud resources for a relatively short period of time. And depending upon your cloud service provider, you'll have different ways of doing that. So in AWS, this would be an IAM role. In GCP, you would use a GKE workload identity. And in Azure, you would be using the somewhat recently released Azure AD workload identity. And again, these are the the proper ways to provide cloud access to a particular application. And you might be a little concerned, well, hey, if this is the right way to do it, is there still an opportunity for me as a pen tester or red teamer to take advantage of it? And yes, there absolutely still is. To figure out how we would do this, we need to talk a little bit about how these are implemented. So in an AWS context, if you wanted to provide an individual pod access to your cloud resources, you'd first have to create a service account for it. And from there, pass in the ARN of the role that you would like that service account to represent. Then when you run your pod, you need to specify the service account name associated with that role. And then finally, at runtime, dynamically, a JWT will be injected into the pod on the file system as /var run secrets. And it's this token that is used and exchanged with the cloud service provider, in this case, AWS, to get those IAM credentials associated with it. Now, it's important to note that for a developer, this is all completely transparent to the application. They don't have to worry about managing this or rotating it or anything like that. If they're using the AWS SDKs, this will all automatically get figured out for them, and it will pull the right identity with the right permissions. But let's say we're intending to do some not so legitimate activities. How can we exchange a token for a cloud identity? Well, we can, if we find a local file inclusion vulnerability, if we get code execution on the pod, if we find any other type of arbitrary file read vulnerability, we can pull that token from the file system and then use the STS assume role with web identity API call, passing in that token as well as the role ARN that we want to assume, and we will get back IAM credentials for that identity, allowing us to pivot into the cloud control plane. Now, other clouds do it similarly and differently, just depending. Azure, for example, does it nearly identical to what I just described with AWS. They simply have a Azure spin on the name of the token, and otherwise has a very similar setup. GCP, to contrast, does it very differently. They actually spin up a GKE metadata server pod within the cluster. And as far as I'm aware, the service there that's running isn't documented, or at the very least, its source code is not publicly available. And that service is what handles the credential exchange for you so that you can reach out to it. When you make a call to the metadata service, there are some IP tables rules that will redirect any calls to that link local address to that metadata service so that it can handle that exchange. So it's important to note, even if developers, quote unquote, do the right thing or use these short-lived credentials and these roles and whatnot, there's still an opportunity there for us as an attacker to take advantage of them and use it for our own purposes. And next, I'll hand it over to Christoph to tell us a little bit about operators.
Thanks. So we'll see a quick demo of that in a bit, but so Kubernetes operators, they are a popular way to basically define an end state that you want to reach, and the operator is going to run a reconciliation loop that is going to basically run continuously to make sure that your end state happens. One popular use case for that is to bring secrets from the cloud to the cluster, and two popular options are external secrets and the secret store CI/CD driver. So the way this works is that you're going to have your operator running in the cluster that's going to be connected to the cloud, and it's going to bring secrets to your workloads. So typically it's going to sync them as a Kubernetes secret that you can then mount easily in your workload, so that your workload doesn't have to handle this, how do I get the secrets from AWS Secrets Manager or from AWS SSM Parameter Store. So the issue with that is that kind of by default, by definition, your secret operator has some level of access to the cloud environment. And if you look at some documentation, some tutorials online, many of them will get a lot of access. So this is an example of a tutorial that says, use this policy for external secrets. So it can access all your secrets, which means that if we are able as an attacker to get access to the secret operator, or to get access to its cloud identity, well, we are able to get access to all the secrets. So let's see a quick demo of that. And here we're going to be as well as before authenticated as a worker node. It's a bit blurry, but hopefully you can see that, should be good. Yeah, let's keep it as is. And we can see that we are authenticated as a worker node. Okay, so we're going to look at the pods, and in the cluster we have a few pods. One of them is external secrets. So what we can do as an attacker is, create a service account token for this service account. There are a few options here that we can basically get through grep, like the pod UID and the exact name of the pod, and we get back a token. So this token is what allows us to authenticate to the Kubernetes API as this external secrets service account. And it's also, as Nick showed us before, what we can use to pivot to the cloud. So if we use assume role with web identity, with this role arm that we can find from the pod definition, so it's just a matter of grep, we get back some AWS credentials that we can see are actually the ones for external secrets role. So we can put that in our shell, and if we do who are we can see that we are indeed authenticated as the external secrets role. And from there, by design of what we are doing, we can access the secrets in the cloud environment, we can get the secrets, and it's kind of game over from there. Great, so on the next slide, this demo should be over. Cool. So what did we just do? Just as a summary, we stole somehow, through one of the techniques we saw before, we stole node IAM credentials. Then we saw that external secrets was running in the cluster. We created a service account token for this pod, and then we exchanged that for AWS credentials, and then we are authenticated as the operator. So this was an example of what to do for secrets operator, but there are many operators. Some of them are going to allow you to define IAM users or IAM roles from the cluster. Others are going to allow you to write CRDs, so custom resource definitions, and then create that as infrastructure in your cloud provider, which means that these tend to be privileged. This is an example from the docs of a popular one that tells you, attach admin access to it, and you can see how this can go wrong. So what can we do in general to make this better? A few things, but mostly trying to minimize the privileges. In the example of secrets, you can assign tags to the secrets that you want to bring inside the cluster, and then only allow you the operator role to read secrets with that tag. And also it's a matter of knowing the pivots that you have and making sure that they are that they make sense to your risk posture. Now, wrapping up a little bit, Nick, you're going to play the role as the attacker again. Can you maybe show us a little bit the different attack paths that we took? And then I will conclude, in terms of the different controls that we can use.
Yeah, absolutely. So from a attacker's perspective, if you're going up against a Kubernetes environment in the cloud, it's important to note that you have a couple options in order to either navigate into the cloud control plane itself, or perhaps trying to escalate privileges into a cluster administrator. If you find yourself able to perform server-side request forgery, there's the opportunity for you to pivot off of a running pod to access the instance metadata service of the underlying node. And from there, there's the potential for us to authenticate as that node. We could either try and pivot into the cloud control plane from there, or perhaps we can create a service account token or try and steal one and use that to authenticate to the pod cluster. And from there, try and retrieve IAM role credentials for other pods, or perhaps we can navigate as a cluster administrator. Now, it's important to note, even if there isn't the opportunity for server-side request forgery, say, for instance, the cluster is using instance metadata service version 2 or some other header-based protection for server-side request forgery, if you get code execution on the host, if you get file read or LFI, you can still interact with that service or exchange tokens for those credentials and still access those resources. So the fix here is not to try and ensure that server-side request forgery doesn't work. It is to prevent the pods from accessing the node's metadata service itself. And that takes us to some defenses.
Right, so this is a bit to sum up, if you are a defender, if you are running clusters, what should you do in a nutshell? So the first thing is to not hardcode cloud credentials. So no AWS access keys in the pod file system, even as a Kubernetes secret, because these, they are long-lived and they are the cause for most of the cloud breaches. So it's much better to use platform managed authentication, which means IAM roles for service accounts in AWS or workload identity in GKE, or Azure ID workload identity, which is GA since April in Azure. Second one is to make sure that the pods, what runs inside of the pod, cannot access the instance metadata service. So for GKE, it's going to be workload identity. And for AWS and Azure, you need to explicitly block the access to the metadata service, typically through a network policy. And the third one is to try to be mindful and aware of what cloud permissions the different workloads have. And this is easier said than done, right? Because if you try to look at your service accounts in Kubernetes and your roles in AWS, you're going to look a little bit like the picture on the next slide, which is you looking at the service accounts, then looking at the trust policies of your roles and trying to figure out which service accounts can use which role. And it's a bit of a hassle. So we try to help with that. And we try to figure out what are the common challenges that people have in managed Kubernetes environments. And there are mostly three that we saw that are a bit mapped to these controls. The first one is, how do you find if what kind of cloud access your workloads have? Second one is, do you have hard-coded cloud credentials in your cluster? And the third one is, are you properly blocking the pod access to the IMDS? So a few months ago, we released an open source tool that is called the Managed Kubernetes Auditing Toolkit, which we say MCAT. And this is currently focused on EKS, but we hope to add GKE as well in the future. And it does exactly these three things. So first thing it does, it looks at your service accounts in Kubernetes, your IAM roles in AWS, and it's going to parse the trust policy of the IAM roles to figure out which of the pods, which of the service accounts can assume it. And so in In a few seconds, you get something like that allows you to see directly your cloud pivots. Second thing is to look at, are there any hard-coded AWS secrets in Kubernetes config map, Kubernetes secrets, or pod definitions with a very low false positive rate? And lastly, let's assume that you blocked pod access to the IMDS. You want to make sure that this is actually working. So it's going to help you with that. Try to spin up a pod, try to access the IMDS through IMDS v1, IMDS v2, and tell you if this is properly blocked. Again, this needs to be blocked, and just enabling IMDS v2 is not enough, because if you have code execution in the pod, you can still do the pivot. So go ahead, give it a try. It's on GitHub, it's free, it's open source. It's a single binary as well, and it uses your authentication context. So if you are authenticated to AWS and to Kubernetes, you don't have to do anything else in terms of setup. So give it a try, and if you have some feedback, you're more than welcome. And in the meantime, thanks a lot. So if there are any questions, feel free to ask, either here or on Slack. We'll be happy to answer them or to start any fun discussions on the topic.